At its core, the difference between SQL and NoSQL boils down to structure and flexibility. SQL, or relational databases, enforce a defined schema and consistent relationships, which is great for predictable data and complex queries. NoSQL, or non-relational databases, on the other hand, relax those rules to handle rapidly changing, varied, or massive data. That design difference shapes everything else. For example, take how you query a database. SQL uses a standard language, SQL itself, with joins and aggregations. NoSQL queries, though, are model-specific and usually simpler. There's also a difference in how you scale them. SQL scales vertically first. NoSQL scales horizontally through partitioning and replication. And then there's consistency. SQL favors strong ACID guarantees. NoSQL often trades strict consistency for availability and speed.
SQL databases are all about structure and guarantees. They store data in tables, where rows represent individual records and columns handle the attributes. There's a schema that defines the whole structure, including which columns exist, their data types, and how tables connect to each other. This schema enforces consistency. It makes sure every record follows the same rules for types, relationships, and constraints. For example, a category name can't be longer than 255 characters, and it must not be null. On the other hand, every product price has to be a decimal, not a string. And the category ID needs to point to an actual existing category in the category table. As you can see, we have strict rules for every single piece of data we want to save in our database. When you perform write operations on data, SQL databases wrap them in an ACID transaction. Let's break it down, starting with C, which stands for consistency. Imagine we have a table to track bank account balances. It has rules like the owner name must be a varchar no longer than 100 characters. The balance must be a decimal value, and it has to stay positive. No negative balances allowed. Consistency means that whenever you insert or update data in this table, it must follow all those rules. If you try to insert something that violates them, for example, withdrawing more money than you have in your account, the database will throw an error and reject it. Next up is atomicity. This means all steps in a transaction must succeed, or none do. For instance, say Alice wants to send $60 to Bob, but she only has $50, and we have that same constraint keeping balances positive. We'd wrap two queries into one transaction. Subtract 60 from Alice's account and add it to Bob's. Both must succeed. If the first one fails because Alice doesn't have enough, the whole transaction gets canceled, and any changes made within it are rolled back, like it never happened. Then there's durability. Suppose Bob deposits $100 into his account, and the server crashes right after. Durability ensures that once a query or transaction succeeds, it's permanently written to disk. So the changes stick around, even through restarts or crashes. Finally, isolation. Picture an e-commerce website with just one pair of limited edition sneakers left in stock. Two customers try to buy it at the exact same millisecond. To prevent race conditions, the first query locks that specific row, forcing the second user's query to wait until the lock is released. While the lock is active, the first buyer completes the purchase, reducing stock to 0. Once done, the second query tries the same thing, but now with 0 items, it fails. So isolation means no interference between different queries trying to modify the same piece of data. Behind the scenes, a query planner optimizes your SQL statements by choosing the best indexes, join orders, and execution paths. Let's go over a simple inner join example, which is the default join type in SQL. It selects records that have matching values in both tables. Imagine we have a Facebook table with users that keeps track of how many friends each one has. On the other hand, let's take a LinkedIn table that shows how many connections each user has. First, when you create and run the following query, SQL creates a new table with columns from both of the tables you're trying to combine. It then looks for values that match between the columns you specify in the on statement. Putting the table name with a period before the column name makes it clear which columns from each table SQL will check for matches. SQL starts with the first value in the specified column of the first table, like Facebook.name, and then scans every value in the specified column of the second table, like LinkedIn.name, for a match. If there's a match, it copies the data from both the row in the first table and the row in the second table, and adds it to the newly created table. SQL won't include any rows that don't have a match. Make sure you know what data you want in the final table so the excluded information doesn't mess up your analysis. NoSQL databases are built for flexibility and scale. Instead of fixed tables and schemas, They store data in models that match your specific use case. Let's say you have an e-commerce website, and you decide to use a traditional SQL database like Postgres. To store product info, you'd use a table like this. At the beginning, you just sell clothes, like different t-shirts. Each t-shirt might have size and fabric properties. In a few months, you decide to expand and add more products. Now you're selling electronics too. But here's the problem. There are no attributes to describe a phone. Well, you would need to take your application down and run a migration on your table to add the necessary columns. So now you can store phones and maybe add processor and storage info for that product. You can see how every time you add a new product, you'd need to add columns. And many of those columns would stay empty because they're product specific. For this kind of use case, you're most likely to choose a NoSQL document database. Every single product or object is self-contained and only has the necessary properties. An iPhone doesn't have fabric attributes, and a t-shirt doesn't have processor ones. You can keep adding new products and spend way less time customizing or migrating your database. Let's take a different example this time and compare it with a columnar database. Let's say we have sales data for an e-commerce website. In a SQL or row-oriented database like MySQL or Postgres, data is stored row by row. All the information for one sale is kept together in a single block on the disk. This layout is best for adding a new sale or looking up a specific receipt by ID. You can think of it as a stack of paper receipts. To read one receipt, you just pick it up and see everything on it. On the other hand, in a column-oriented database like BigQuery, Snowflake, or ClickHouse, data is stored column by column. All IDs are together, all product names are together, and so on. This layout is best for analytical queries, like finding the total revenue or average price. You can think of it as a set of specialized ledgers. One book only lists prices, another only lists dates. Now, if you mostly use your data for analysis, column-oriented databases will be significantly faster for calculating averages, sums, or trends. And here's why. First, it's much more I/O efficient. If you want to calculate the total sales amount, a row-based database has to read every single row into memory, including the product names and dates, just to discard them and grab the amount field. A column-oriented database, though, reads only the amount column from the disk. This drastically reduces the amount of data the computer has to move. Also, in a column, the data types are frequently the same. For example, in the date column, you might see the 2nd of January 2024 repeated. Columnar databases use algorithms like run-length encoding to store this as the 2nd of January 2024 x2, which takes up almost no space. Smaller data on disk means faster reading. And finally, there are some hardware optimizations they can leverage as well. SQL and NoSQL each excel at solving different problems. The key is understanding the trade-offs you're making. Let me share a few advantages of SQL. First, structured data. It enforces rules and relationships through a fixed schema. Second, powerful querying. Joins and aggregations make complex analysis straightforward. Third, strong consistency. ACID transactions keep your data accurate and reliable. Fourth, mature ecosystem. It offers long-standing tools, frameworks, and community support. Now, a few disadvantages. 1. Rigid schema. Changes often require migrations or downtime. 2. Scaling limits. Vertical scaling is simpler than horizontal sharding. And finally, overhead for simple workloads. It can feel heavy for small or unstructured data. Now let's dive into the advantages and disadvantages of NoSQL databases. Starting with the advantages, flexible structure. Its schemaless design is ideal for data that's constantly evolving or comes in all sorts of varieties. Horizontal scalability, sharding, and replication make it supernatural to scale out by just adding more nodes. High availability. The system keeps serving traffic smoothly, even if a node fails. Strong performance. For specific access patterns like quick lookups by known keys or partitions, it's incredibly fast. Now, on to the disadvantages. Weaker consistency. With eventual consistency, you might occasionally see stale or outdated data. Limited querying, no built-in joins here. For complex queries, you'll need to add custom logic. And finally, less standardization. Each NoSQL database comes with its own unique query language and behaviors, so there's no universal standard. In summary, NoSQL shines in flexibility, scale, and speed for certain use cases. but it sacrifices some of the rock-solid consistency and querying ease you get with traditional relational databases. In conclusion, there is no right or wrong. Each database type is optimized for a specific use case.